Hello students, welcome to the next lecture of the ordinary differential equation. In the last lecture we talked about the linear differential equation and its solution. Today we will talk about the equations that are reducible to linear differential equation. So let us see what are such type of equations. So first we need to understand that the equations of type dy by dx plus py is equal to q dot y to the power n. These are the equations that can be reduced to linear differential equation. So these are there is a very slight difference from the actual linear differential equation. This is not the linear differential equation, but we can reduce this to the linear differential equation. So how we can reduce this to the linear differential equation, let us see. If you can see on the right hand side, this is q dot y to the power n. If you remember, on the right hand side, this was q, which was free from these values of y. So we have to convert this so that the q is free from the values of y, as well as the p should also be free from y. So what we'll have to do, let's see step by step. Step 1, we need to divide this equation by y to the power n. So first we'll divide this equation by y to the power n. So this will become 1 upon y to the power n dy by dx plus p upon y to the power n minus 1, because we had a y in the numerator. So this is y. So whenever we'll divide this by y to the power n, so this will become in the denominator y to the power n minus 1, and this will be cancelled out. So the first step is to divide the equation by y to the power n. Now the second step is to substitute 1 upon y to the power n minus 1 by z. This is another variable, a new variable. So we will convert the equation into the linear differential equation of two variables x and z. So this is a new variable z. So next is this substitution, 1 upon y to the power n minus 1 is equal to z. So and on differentiating this, we will see that y to the power minus 1 dy by dx will be replaced by dz upon dx. We have to replace both the things, dy by dx also, because we need to convert the equation into two variables z and x. Just by doing these two substitutions, you can see this 1 upon y to the power n dy by dx will become dz upon dx, and 1 upon y n minus 1 will become z. So just by performing these two substitutions, we can see that the equation is converted. So this is dz by dx plus p of z is equal to q. Now this is a linear differential equation in two variables x and z. So this is how we can convert, or how we can reduce the equation to the linear differential equation. And once we have converted the equation to the linear differential equation, we will solve this by the same method we used to do for the linear differential equation. So let's see one example based on this question. So this is a question: solve x square dy plus y x plus y dx is equal to 0. So first we will write this equation into this form, into the form similar to the linear differential equation. So we can see we are converted this into dy by dx form. So this is x square dy by dx minus yx minus of y square. So finally this is something x square dy by dx plus yx is equal to minus of y square. So you can see this is similar to linear differential equation, but this is not actually linear differential equation. So we need to reduce this to the linear differential equation. So what we'll have to do for the reduction, first we will convert this into this equation, which is to be reduced to linear differential equation. So we have just divided this equation by x square, and this is dy by dx plus y upon x is equal to minus of y square upon x. So now you can see this is dy by dx, and now this is p of y, where p can be considered as 1 upon x, and this is q of y to the power n, where q can be considered as minus of 1 upon x square. Then y to the power n here will be y square. So what we'll have to do, step 1, we will divide this equation by y to the power n. In this case, y to the power n is y square. So first we have divided this equation with y to the power 2. So once we will divide, you can see this is the new equation. Now from this new equation we need to substitute this value. So this is 1 upon y. We always substitute this value leaving x. So we'll substitute this by another variable z. So this is the substitution. So you can recall the second step of reduction. So this is the second step of reduction. So we'll substitute this, and just for the substitution we need to find out the value of dy by dx also. So this is 1 upon y is equal to z. On differentiating this equation with respect to x, this will become minus 1 upon y square dy by dx, and this is dz upon dx. So from which we can find out the value of dy by dx. So just by replacing the two values, one is 1 upon y as equal to z, another is dy by dx in the form of dz by dx, the given equation becomes to this minus dz upon dx plus z upon x is equal to minus of 1 upon x square. Arranging the minus sign, this is actually dz upon dx minus z upon x is equal to 1 upon x square. So now this is the equation reduced to linear differential equation, and we can see this is a linear differential equation in two variables x and z. So this is dz upon dx, this is minus z upon x, and this is 1 upon x square. This is q, which is free from y. So from this equation p comes to be minus of 1 upon x, and q comes to be 1 upon x square. So we have to recall the definition of linear differential equation, where p and q have to be the functions of x only and are to be free from y. So let's continue. So just to solve this linear differential equation, we will calculate the integrating factor. Here the integrating factor will be e to the power integral of p dx, where p is 1 upon x, we have just calculated. So integral of 1 upon x will be log of x, and e to the power log of x will finally be x. So the integrating factor comes to be x. Now we need to multiply this with this z and the solution. So we need to recall the solution. Z multiplied with integrating factor, integral of q multiplied with integrating factor. So this is integrating factor, this is q, this is p, and this is integrating factor. Now we need to solve this. So this is a simple integration we can perform, and just by doing the integration you can see this comes to be z dot x log of x. Now we'll replace this z back. So this will be x upon y is equal to log of x plus finally the integration constant c. So this is the solution of the given equation. Let's take a quick look to another question, one more question based on the same topic, that is reducible to linear differential equation. So we can see this is the question given: x dy by dx y log y is equal to xy e to the power x. So first of all we need to convert this to the similar equation, to the linear. So we have divided the equation by x. So this is dy by dx is equal to y log y upon x is equal to y dot e to the power x. Now this is not a linear differential equation, so we need to find out y to the power n onto the right hand side. So this is the factor y to the power n, from which we'll have to divide the whole equation. So just by dividing by y the whole equation, so this is 1 upon y dy by dx plus log y upon x is equal to e to the power x. So now we need to perform the second step of reducing, that is substitution. So what we used to take into the substitution, the term with x here. So log of y will be substituted. So log of y is substituted as z, and on differentiating this will give 1 upon y dy by dx is equal to dz upon dx. So from this equation we can replace dy by dx also. So the equation becomes dz upon dx plus z upon x is equal to e to the power x by performing these two substitutions. One log y is z and the other is this. So just by performing these two substitutions, the equation becomes dz upon dx plus z upon x is equal to e to the power x. Now we can compare this with the linear differential equation, that this is similar to the linear differential equation, and we need to solve it. Use the same method. We need to find p. So p is 1 upon x free from y, only the function of x. Q is also e to the power x free from y, only the function of x. So in that case we need to find out the integrating factor. The integrating factor is always e to the power integral of p dx. Here p is 1 upon x, so this comes to be x. So integrating factor comes to be x. Now we'll simply write the solution of the linear differential equation. So solution is z dot x is equal to integral of e to the power x dot x dx. If you do not know how to write the solution of linear differential equation, please watch my previous video how we solved the linear differential equation. So we have just written the solution and performing this simple integration. So we just integrate this value product, we'll use the product rule, and finally by replacing this z, so this comes to be log y x is equal to x dot ex minus e to the power x, and finally plus a constant of integration. So that's how we can reduce the linear differential equation. We can reduce the normal equation into linear differential equation and can find the solution of such ordinary differential equations. In the next lecture, we will see the solution of exact differential equations. Thank you so much.